Hello everyone. In this lecture, we are going to discuss about the fixed axle load approach or the fixed vehicle approach for the analysis of traffic for bituminous pavement design. So these are the references. You have the pavement analysis and design by Huang and the principles of pavement design by Yoder and Witzak. So the fixed axle load approach of traffic analysis is that the pavement design will be governed by the number of repetitions of a standard vehicle or a standard load. Usually, a 80 kilonewton single axle dual wheel is considered as a standard load. So all the different classes of axle loads and axle load configurations are converted to an 80 kilonewton single axle dual wheel load assembly, and the number of repetitions of this will be over the design period will be considered for the design of the flexible pavement. Okay. Now, in order to do this conversion of different classes of vehicles or different classes of axle loads to a standard axle, you use something called an equivalent wheel load factor. So the definition is equivalent wheel load factor defines the damage per pass which is caused to a specific pavement system by the vehicle in question relative to the damage per pass of an arbitrarily selected standard vehicle which is moving on the same pavement system. Or you can define it as a damage per pass to a pavement by the axle in question relative to the damage per pass of the standard axle load. Okay. Now let us discuss about the passage of vehicles on a pavement system, or how this vehicle repetitions are to be considered, or how the vehicle wander is to be considered. So a plot is made here with the lateral distance of the pavement from the edge. So let's say this is the edge of the pavement and this is the lateral distance from the edge, and the frequency of load distribution of different classes of vehicles is plotted here. Say for example, we consider two vehicles J1 and J2 which travel on this pavement. You can see that the load distribution will form a more or less a normal distribution, with the mean load distribution is at a distance of xj1 from the left end of the or from the edge of the pavement, and xj2 represents the main location of the load distribution of the second class or the J2 class of vehicle. Okay. Now, each vehicle is assumed to wander laterally in the pavement system such that they stress or strain repetitions of the jth vehicle along a pavement interval of a small section of x can be denoted as f, j, ix, okay, which means that I am considering say J1 class of vehicle in a small distance of x in the pavement. Let the frequency of load stress or strain application is given by this small f letter. Okay. So this is the distribution for the first vehicle and this is the distribution for the second vehicle here. Now let us assume that NF is the number of repetitions to certain failure for a vehicle class on a specific pavement system. Let us assume that each vehicle class has NFJ number of repetitions, or the number of repetitions to failure is noted as NF on a particular pavement system. Now, if there are NFJI passes of a vehicle which causes damage or failure, then the damage per pass of each vehicle can be, or it is denoted as unit damage, can be written as DJI is equal to 1 by NFJI, where JI represents my vehicle class and NF is the number of repetitions to failure and small d represents the damage per pass. Now, the equivalent wheel load factor as we defined is the damage caused by the jth vehicle or the vehicle in question to that of the damage caused by a standard vehicle. So, equivalent wheel load factor for the jth vehicle, or it is denoted as capital FJ, can be denoted as dj by ds, where s indicates the standard vehicles. So, since the number of repetitions to vehicle failure and the damage per pass are inversely proportional, you say that the equivalent wheel load factor is equal to the number of repetitions to failure of the standard vehicle by the number of repetitions to failure of the jth vehicle. Okay. Now, Let us say that small nj represents the number of passes for one vehicle class of j in a time interval of t. And fjx, as we already discussed, is the stress or strain repetitions of the jth class in a small distance of the payment, say x, which is see in this picture, which is denoted as this a minus b, or the small distance of x. Okay. Then the total damage that is accumulated by this vehicle class j in a time t on the small payment interval of x is given by the damage per pass, which is dj, into the number of repetitions into the frequency of strain repetitions of, or the stress or strain repetitions, which is fjx. So the total damage is given by dj for the jth class of vehicle, dj nj into fjx. Now suppose you consider different classes of vehicles. So j is equal to 1 to capital J. Then for a small interval of, or a small payment interval of x for a duration of time t, the total damage that is caused is dtx is equal to, in that why it is written as dtx is for a time t in a small payment section of x, the total damage accumulated can be written as sigma j is equal to 1 to capital J of dj, nj and fjx. Okay. Now we have the equivalent axle load factor given as dj by ds, or small dj can be written as fj into ds. Now substitute it in this equation number 4, we get the total damage accumulated is from all the vehicle classes for a time t in a small payment section of x distance is equal to sigma j is equal to 1 to j nj fj ds into small fjx. Now, suppose you are considering the standard vehicle. Now, the equivalent repetitions of the standard vehicle occurring in time t can be written as NE is equal to the total damage divided by damage per pass of the standard vehicle. Okay. So, because this is dtx represents the total damage, and if I say that small ds is the damage per pass of a standard vehicle, the number of repetitions of the standard vehicle for failure can be obtained like this. Now substituting for dts, we know that NE is equal to, you can you can remove this ds. So NE, which is the number of repetitions of the standard vehicle for a time t on a distance of x for failure, is equal to nj fjx into fj. So what you see is that this equivalent repetitions of the standard vehicle is, it's a variable across the payment width. Now, so for at various payment widths, if you consider, you will get different number of repetitions for failure. And for as far as the design is considered, we are interested in finding what is the maximum number of repetitions which can lead, which can cause failure. So NE, that is for the design, the number of repetitions is taken as maximum of this NJ, FJX and FJ. Now, if in the case of an airport payment, it is very reasonable to consider this vehicle wander over the payment section, whereas in the case of highway payments, it can be assumed that all these vehicle types will stress or strain the same point for during every load application. So what you can see is that in this distribution of load, this distance is constant, or xji for the ith vehicle is constant for all classes of vehicle, so that you can take this frequency of fjx, that is the the frequency of stresses of strain can be taken as unity, so that the number of repetitions of the standard vehicle occurring in time t can be written as sigma j is equal to 1 to j of nj fj. Okay, now let's see how this, so this represents the number of repetitions of the standard axle. Now let's see how this equivalent axle vehicle or equivalent wheel load factor can be used in the in the analysis of traffic for payment design. So as we have already discussed, the equivalent wheel load factor Fj is the damage per pass of a vehicle in question to the damage per pass of the standard vehicle, or it is the number of repetitions to failure due to a standard vehicle by number of repetitions to failure due to the vehicle or the axle in question. Okay. So EWLF, or the equivalent wheel load factor, is a function of the number of repetitions to failure, right? So it is a direct function on what failure criteria you are going to discuss. Also, it will depend upon the type of the payment and also the thickness or the structural capacity of the payment. Now, as far as the highway payments are considered, you take an 80 kilopounds or an 80 kilonewton single axle dual wheel assembly is taken as the standard axle, as you can see here, each wheel having a load of 20 kilonewton. So, a total 4 wheels having a total load of 80 kilonewton or 18 kilopounds is considered as the standard axle. Now, as I said, the EALF, the equivalent axle load factor, will depend upon the failure criteria that we use for payment design. So, this is the typical payment cross section taken from the IRC 37 2018. The two critical strains or the two critical failure mechanisms that are considered for the payment design as per IRC 37 as one is the rutting in the payment structure, and the second one is a fatigue cracking. Okay. So, as far as the rutting is concerned, so fatigue cracking. So, for fatigue cracking is related to the tensile strain at the bottom of the bituminous layer, and the rutting of the pavement structure or the subgrade rutting is related to the vertical strain on top of the or vertical compressive strain on top of the subgrade, right. So, let us see how this equivalent wheel load factors are determined or equivalent axle load factors are determined from the failure criteria. As I said, the two failure criteria that normally adopted are one is the normally considered are the fatigue cracking and the rutting. Now, the failure criteria for or the distress transfer function for fatigue cracking is given by NF is equal to F1 epsilon T raised to minus F2 into E1 raised to minus F3. So, this is a distress transfer function for fatigue cracking, where NF represents the number of repetitions to failure due to fatigue cracking. Epsilon T is the tensile strain at the bottom of the asphalt layer, as I have already shown you, and E1 is the modulus of the asphalt layer. Of the three coefficients here, F1, F2 and F3, F2 and F3 are the exponents that are to be determined from the material behavior from the fatigue test, and it is seen that the F2 varies from 3 to 5.67 from 671 from various studies, whereas F1 is that parameter that indicates the shift of the performance of the material in the laboratory to the number of repetitions to failure as observed in the field. From this expression, from studies, it is observed that the effect of the modulus E1 is less compared to the effect of tensile strain on the number of repetitions to failure, and hence this E1 factor can be neglected, so that your number of repetitions to failure is proportional to the tensile strain at the bottom of the asphalt layer or epsilon T. Now, EALF is defined as the number of repetitions to failure of a standard axle, which is in this case the 18 kilopounds axle. So, NF18 divided by the number of repetitions to failure of the load in question or the axle in question. So, if it is NFX, so the ratio will give you the equivalent axle load factor, or since they are inversely proportional, this becomes inversely proportional to the tensile strain at the bottom of the asphalt layer. You can write this expression as EALF is equal to epsilon T of X, the vehicle, divided by epsilon T of the standard axle, which is 18. So, epsilon T 18 raised to F2. Now, Deacon has given a value of F2 is equal to 4, so that EALF can be defined as the tensile strain of the vehicle in question or the axle in question by the tensile strain due to an 18 kip axle raised to 4. And NFX and NF18 are, as already discussed, the number of repetitions to failure due to an X-axle load application and the number of repetitions to failure, fatigue failure due to an 18 kilopounds single axle load application during a time T. Okay. Now, since the strains are directly proportional to the loads, you can write EALF as also equal to the load of the X-axle divided by load of the 18 kip axle, which is 18 kilopounds raised to 4. Now, this is for a single axle dual wheel. Now suppose you have to consider the tandem or the TRIDEM axles as well. Instead of writing 18, you can just write it as LS, which is a load due to the standard axle. So the equivalent axle load factor can be written as LX by LS raised to 4. So this is that factor which can be used to convert different axle loads to a standard axle load. Now coming to the second criteria. So the first criteria that we have discussed is the failure criteria due to fatigue cracking. Now let's see the failure criteria due to the permanent deformation or rutting. The distress transfer function is given as ND is equal to F4 epsilon C raised to minus Fy, where ND is the number of repetitions to failure due to permanent deformation and epsilon C is the compressive strain on top of the subgrade, as we have seen from that figure. Okay. Now different studies have found out different coefficients or values for this F4 and F5 parameters, and Asphalt Institute has given a value of F5 as 4.477, Shell has given a value of 4, and UK Transporter Road and Research Laboratory has given a value of 3.95. So on an average you can take a value of 4, so that the equivalent axle load factor again becomes the number of repetitions to failure due to the 18 kip axle by number of repetitions to failure due to this the axle in question, which becomes epsilon C of x by epsilon C of 18 kip raised to 4. So this becomes the EALF if you are considering the permanent deformation or rutting as the failure criteria. So from this EALF analysis using the failure criteria, what we have seen is that the equivalent axle load factor for any class of vehicle in question is equal to the stress due to that class, which is the ith class, divided by the tensile stress due to the ith class divided by the tensile stress due to the standard axle raised to 4, which is approximately equal to the tensile strain of the ith class of vehicle divided by the tensile strain of the standard axle raised to 4, which is approximately equal to the compressive strain of the ith axle or the axle in question by the compressive strain of the standard axle raised to 4, which can be approximately equal to the load of the ith axle or the axle in question divided by the load of the 18 kilopounds or the 80 kilonewton axle load raised to 4. So this is a fourth power relation which is used to convert the axle load in question to a standard axle of 18 kilopounds or 80 kilonewton. Now coming to the analysis of the tandem axle loads or a TRIDEM axle load. Now we have large spacing between the two axles of a tandem axle, right? So the critical tensile or the compressive strains under the multiple axles will be different from that of a single axle, right? So in order to find the EALF, you need to see whether the damage caused by a tandem axle is same as that of a damage caused by a single axle, or whether the damage caused by two axles of a tandem axle is twice the damage caused by a single axle. Okay. So accordingly, your tandem axle or a TRIDEM axle, the EALF factors will vary. Now, for tandem axle and TRIDEM axle, the effect of this additional axles on the tensile strain at the bottom of the asphalt layer will be quite different from the compressive strain at the top of the subgrade. So, which means that if you are considering a tandem or TRIDEM axle, the effect or the effect due to a fatigue cracking criteria and a subgrade rutting criteria may not give you the identical results as you have discussed here. So here in the case of a single axle dual wheel, we have seen that the criteria based on the tensile strain or the fatigue criteria, fatigue cracking criteria, or the criteria based on the rutting criteria is more or less the same, but it may not be same in the case of a tandem or a TRIDEM axle. So in such case, we can find out whether in order to get the EALF, you can use a damage analysis concept. So this concept is also being discussed in detail in this course. I'll just quickly go through what this damage analysis is all about. So in order to find the EALF based on the damage analysis, you can see that EALF is, or the equivalent axle load factor, is the ratio of the damage ratio due to a tandem or a TRIDEM axle to the damage ratio due to a single axle. So this ratio can give you the EALF corresponding to the tandem axle or a TRIDEM axle with respect to a single axle. Okay. Now, how to get this damage ratio? The damage ratio is essentially the ratio between the predicted and the allowable number of load repetitions computed for each load group in each period and summed over a year. Okay. So, as you can see from this expression, damage ratio is given by sigma I is equal to 1 to P, J is equal to 1 to M of Nij by capital Nij, where small nij is the predicted number of load repetitions for a load class J in a period of I. Okay. So, this is the load that is predicted in the traffic or in the actual scenario, what is the traffic it is there, and divided by what is this capital Nij is the number of load repetitions that are permitted or allowable based on the failure criteria. So, you have two criteria, one is the fatigue cracking criteria and the rutting criteria. So, based on that, what is the number of repetitions that are allowable. So, this ratio you can sum it up for all classes of the vehicles. So, that is J is equal to 1 to M, and sum it up for the different periods. So, you have like different periods in a year. So, for different periods you can have different criteria for or different number of repetitions to failure. So, sum it up for different periods. So, you get I is equal to 1 to P, you get the damage ratio. So, from this damage ratio, if you find it for the tandem or TRIDEM and divide it by that to a single, you can find the equivalent axle load factor. Now, how to get this damage analysis, how do this damage analysis for tandem axle? So, you have to find out the number of repetitions to the predicted, so the allowable number of repetitions, right. So, in order to get the allowable number of repetitions due to the two criteria, you need the epsilon T and the epsilon C value. But you have like a tandem axle with dual wheels, you have like 4 number of wheels. So, you have to see where you find this epsilon T and epsilon C and what value is used in the distress transfer function is important. Okay. So, let us say here I have shown a tandem axle. This is a tandem axle with 1 and 2 are the wheels, one side of a tandem axle, 1 and 2 are the 2 wheels and 3 and 4 are the other wheels with the tandem spacing of ST. Okay. So, the ST is the tandem spacing. Now, what you have to do is that you have to get the number of repetitions of failure using the two failure criteria. So, you have to determine the tensile and the compressive strains. So, for which first of all you will consider points 1, 2 and 3 under a single axle. So, under the first axle. So, you can see here this is point number 1. So, remove this. Okay, this is point number 1 which is at the center of the first load. And point number 2 is edge of the first load, and point number 3 is midway between the two wheel loads. So, you see that you have 3 locations. At these 3 locations, you will find what is the tensile strain and the compressive strain. And you can find the maximum of the 3 so that you will get the, so let it be epsilon A. So, under the first axle you can find the maximum of these 3 strain values, and that can be used to find the allowable number of load repetitions due to the first load. Okay. Now, the second points that you have to consider is midway between the two axles. So, this is axle number 1 and this is axle number 2, and ST is the spacing between the two axles. So, midway between them you have to find out three points. One is at this comes close to the center of the wheel loads, the other is midway between 1 and 3. So, you can choose 3 points, and at these 3 points also you have to consider what is the strains and the strain that, so you can see here at midway between the two axles the strain comes to be epsilon B, and you have an effect of the other 2 wheels as well. So, you have the effect of this wheel as well as the effect of this wheel. So, what you have to do is that the axial strain that has to be considered for the computation of the allowable number of load repetitions is epsilon A minus epsilon B. So, essentially you are finding 2 sets of number of repetitions of failure. One is at any one point in this 1, 2, 3 location, and the second one is at any one point in these 1, 2, 3 locations, or whichever point is the highest value. So, for the first set of the first location, the value that you have to consider is maximum of the strain at point 1, 2 or 3, and in the case of the second location, you have to take epsilon A minus epsilon B, where epsilon A is the load under the first load and epsilon B is the load that comes at the midway. Okay. So, that is how you will take the strains for finding the number of repetitions, or using in the fatigue and the rutting equations to find the number of repetitions to failure in the case of a tandem load. Now, in the case of a TRIDEM axle load, so you have, this is one axle, this is a second axle and this is a third axle. A similar approach has to be done for the damage analysis. First of all, under one wheel you have to see the 3 points and you have to get the maximum strains under this. And for the second case, you have to take midway between two axles, and for this these points you have to find what is the epsilon A minus epsilon B, as I have shown in the previous figure. And at this point also, here also midway between the two axles you can find an epsilon A minus epsilon B. So, these three values, epsilon A and essentially epsilon A minus epsilon B, are to be used in the distress transfer functions for the fatigue as well as for permanent deformation, and then find the number of repetitions to failure. So, this is how the damage analysis is done for a tandem axle and for a TRIDEM axle. So, you can use, you do not have to check the charts to find these values. You can use Kendler software, which is already discussed in this course. So, you can use Kendler to do this damage analysis. I have just shown some screenshots of using Kendler. So, you can see that there is a damage analysis tab is there, wherein you can give the FT1, FT2, FT3 are the fatigue coefficients, and L and BT is the layer number for which the bottom tension is considered for the fatigue analysis. So, in this analysis, the Asphalt Institute coefficients are used for FT1, that is FT1, FT2, FT3 essentially indicate F1, F2, F3 in our fatigue equation. And then you can use then this is a rutting equation where the F4 and F5, these parameters are given. So, you can see here, and then this is the predicted number of traffic. So, you have three different load groups. The total number of load repetitions for each load group during the design period is given. So, this is from the traffic survey that you have arrived at this number, and that number is the predicted number for the n number of design years. So, that is given. And this is one example of the damage analysis that is done. This is taken from the Huang textbook. So, this is essentially to make a comparison of how this equivalent wheel load factors will differ for a TRIDEM axle and a tandem axle, is what we want to see from this analysis. So, let us discuss this. So, as you can see here, there are two pavement thicknesses are considered in this study. One is a 2-inch thick pavement and the other is a thicker one, which is a 12-inch pavement. Okay, and the single axle that is considered in this study is having a 18 kilopounds axle load with dual tires, and with a pressure of 100, the contact pressure of 100 psi pounds per square inch, and a dual wheel spacing of 13.5 inch. Now, so as you can see here, this is okay. This is the single axle dual wheel that is considered in this study, and for the tandem, this is the same thing is repeated. Okay, so the same load is repeated to get a tandem once, and once again it is repeated to get the TRIDEM. Okay, so that the total load in a tandem comes to twice 18, which is 36 kilopounds, and the TRIDEM load is 54 kilopounds. Okay, and in the case of tandem and TRIDEM, the axle spacing is given as 48 inch. And this is a two-layer system, and for the pavement layer, the pavement layer is considered to have a modulus value of 450,000 psi and a Poisson's ratio of 0.35. Now, there are two structures are considered. One is having a lower subgrade modulus value, that is on a weak subgrade or a weak foundation, having a subgrade modulus of 5000 psi, and the second one having a strong subgrade having a subgrade modulus of 30,000 psi. So essentially you are considering two payment systems with 2-inch and a 12-inch on a weak subgrade and on a strong subgrade. Okay. So this is the failure analysis. As I said, the criteria is selected is the parameters or the distress function of Asphalt Institute is used, and a damage analysis is done, and the damage ratios are computed. For a single, so you can see from here, this table 6.5 is the damage analysis that is done for the fatigue cracking criteria, and the figure, the table 6.6 indicates the permanent deformation criteria. Okay. So these are the two failure criteria for which the damage analysis is done. So this is the damage ratio. As you can see, the 18 kip single axle, the damage ratio is given as 1.311 into 10 raised to minus 4 on a 2-inch payment with a 5000 psi subgrade modulus. Whereas in the case of 30,000 psi subgrade modulus, your damage ratio is 7.03 into 10 raised to minus 6. As we have already mentioned, I will just quickly show you what is the damage ratio. Damage ratio is the number of predicted number of load repetition divided by the allowable number of load repetition for the failure criteria that you have considered, okay, for its fatigue or permanent deformation. So small n, that is where do you get this predicted number? This predicted number is the traffic that is predicted, and we have already input for different load groups what is the total number of vehicles that are expected. Okay, so that load repetition is Nij, small Nij, and capital Nij is what you get from the distress transfer function by capturing the strains at the critical locations. Okay. So for the 36 kilopounds tandem axle, we see that there is a primary damage ratio and a secondary damage ratio and a total damage ratio. As we have already discussed, you have to consider two locations and get the damage ratios and find the total. So this is the total damage ratio if you are considering a 36 tandem axle, and a 54 kilopounds TRIDEM axle, you can see that this is the total damage ratio. Now equivalent axle load factor for this tandem. So this is actually the tandem axle. The equivalent axle load factor can be obtained as the total damage ratio of the tandem to the total damage ratio of the single axle. So this is essentially 2.42 into 10 raised to minus 4 divided by 1.311 into 10 raised to minus 4 will give you 1.85 as the equivalent axle load factor of the tandem axle. Likewise, the TRIDEM axle has a equivalent axle load factor of 2.65, which again is obtained from the ratio of the damage ratio of the TRIDEM to the damage ratio of the single axle. Okay. Now, for each of these payment structures that we have considered, you can see that these are the equivalent axle load factor for the tandem and for the TRIDEM based on this damage ratio computation, and this is using fatigue cracking as the criteria. Now, similarly, you can consider the permanent deformation criteria, wherein you have the equation as related to the epsilon c value. So, using that value, the damage ratios are computed, and from the damage ratios you can get the damage ratio for the single axle, then the damage ratio for the tandem axle, and the ratio of that will essentially give you the equivalent axle load factor for the tandem axle. And also you can see that this is the equivalent axle load factor for the TRIDEM axle for the first payment structure, and the second is a 2-inch payment on a 30,000 subgrade modulus subgrade. So you see these are the equivalent axle load factors. Okay. So we will note some of the observations from this analysis. See, the first one is, so in this study there is a thin payment and a thick payment, right? So the thin payment is a 2-inch payment and the thick payment is a 12-inch payment. So what is observed is that for the thin payment in a weak subgrade, so the weak subgrade is the one with 5000 psi and the strong subgrade is the one with the 30,000 psi, okay? So for the thin payment in the weak subgrade, we see that the damage ratio due to the permanent deformation is greater than the damage due to fatigue cracking. As you can see here, whether it is for a single axle or for a tandem or a TRIDEM axle, we see these green numbers, okay, the green boxes. You see that this is 1.311 into 10 raised to minus 4, whereas in the case of a permanent deformation criteria, we see that it is 3.2 into 10 raised to minus 3, which is much higher, okay. Whereas in the case of a thick payment on a good subgrade, see these values here. So this is a thick payment on a good subgrade. We can see that the damage ratios due to fatigue cracking is greater than that due to the permanent deformation. As you can see, so this first table is for fatigue cracking and the second table is for the permanent deformation criteria. So you see that this damage ratio, whether it is for a single axle or a tandem axle or a TRIDEM axle, we see that these values are higher than the values due to permanent deformation. So essentially what you can note is that the design has to be controlled by the fatigue cracking criteria if it is a stronger payment, as you can see from here, and whereas if it is a weaker payments, as you see here, this is a thin payment, so the weaker payments, this has to be, or the design has to be controlled by the permanent deformation, okay. So this is what is observed from this analysis. And further, you can see that in a 2-inch payment with 30,000 psi subgrade, the strains due to one axle load is not affected by the other axle loads. See, what you can see here is that, which means that if I consider a tandem axle load, you can consider it as 2 single axles, close to 2 single axles, and if you have considering a TRIDEM axle, you can consider it as 3 single axles, which means that the strains that are caused by one axle is not affected by the strains caused due to the other axle loads. So see, you see here that the EALF factor is 1.97, which is close to 2, and EALF factor for the TRIDEM is 2.94, which is close to 3. So this is approximately 2 and this is approximately 3 when you are using a fatigue cracking criteria, and also when you are using the permanent deformation criteria, you see that EALF of this is close to 2, that the EALF of a tandem axle is close to 2, and the EALF, equivalent axle load factor, for a TRIDEM axle is close to 3, okay. So what we observe is that each of these axles are actually acting differently. So one axle and then the next one axle causes certain damage, and then the next axle causes, they are not, there is not much of an overlap between these its behavior. The different axle loads begin to interact when the payment becomes thicker. So as you see here, these values have changed, that is the equivalent axle load factor has changed when you are considering a 12-inch payment. So what is highlighted from this analysis is that the EALF factor essentially will depend upon, or the equivalent axle load factor that we use to convert a tandem axle or a TRIDEM axle to an equivalent single axle load will depend upon the payment structure, what is the thickness of the payment layers, and the criteria that you are using for finding this EALF, whether it is a rutting criteria or the fatigue cracking criteria. Now, as far as the design as per IRC 37 are concerned, these load equivalency factors are given by certain standard values like this, which is midway between your 2 single axles or an single axle load. So as you can see here, if it is a single axle with a single wheel on either side, so if I draw it here, so in this case the standard axle load is taken as 65 kilonewton, so that the equivalent axle load factor can be determined as axle load of the load in question divided by 65 raised to 4. So this will give you the equivalency factor. Whereas if you have a single axle with a dual wheel on either side, the equivalency factor, or the standard load is taken as 80 kilonewton, as we have already discussed. So the load in question divided by 80 raised to 4 will give you the equivalency factor or the load equivalency factor. Similarly, in the case of a dual wheel tandem axle with dual wheel on either side, so I'll just note it like this, and okay, so this is the one. So this is a tandem axle on dual wheel like this. So you have to consider a axle load, the axle load in question divided by 148 is taken as the standard axle load. Similarly, in the case of a TRIDEM axle with dual wheel on either side, 224 is taken as the standard axle load. Okay. So, you can use these expressions and the fourth power law to find the equivalency factors as per the IRC 37. This is discussed in detail when the design using IRC 37 is discussed in this course. Okay. Now, as far as the so these equivalency factors or these parameters F2, F3, F1, etc., F4, F5, etc., are determined based on the road test as well as the field test as well as the laboratory investigations. Now, from the AASHTO road test, the Asphalt Institute load equivalency factors are given. Again, this is based on that power raised to 4 expression for different axle loads from 1000 to, okay, this is the table. So, this table continues. So, this is still 40,000 and this continues from 41,000 to 80,000. We have the equivalent axle load factors or the EALF factors for single axles, tandem axles and TRIDEM axles are given in the AASHTO road, the Asphalt Institute's design approach. Okay. So, this again will be discussed when we discuss the design of the payment based on this approach. So, what we have to summarize, what we have discussed is how the single axle load or the how a single axle load can be converted to a standard axle, how a tandem axle or a TRIDEM axle can be converted to its equivalent standard axles in the fixed axle load approach. Okay.